So in this section, we're going to go over curl and divergence, which are basically operations that we can do on a vector field. And each one of these is potentially going to tell us something about the vector field or if there are any properties to it. So I'm going to go over first a couple definitions and then the actual way we compute these two concepts. So the first is something you've already seen. We've talked about taking the gradient of something. That notation we've been using is really something called our del operator. So the del operator is defined by exactly that upside down triangle we've been using. So this is a vector as a result. It is the partial with respect to x in the first component, and it is the partial with respect to y in the second component. If we're specifically working in R2, and then if we're working in R3, then that third component is the partial with respect to z. Okay. So to give you an example, just working with this, again, you can have this act on a function. So if our function f of x, y, z is given by x squared y, z, then really if I apply this del operator on the function, it is finding the gradient. So the first component would be I take the partial with respect to x of the function. Then I take the partial with respect to y of the function, the partial with respect to z of the function. So in that first component, the partial with respect to x would be 2x, and the y and z stay attached. The partial with respect to y just deals with this, so that derivative is 1. So you're left with x squared z. And then likewise, if I take the partial with respect to z, that's 1. So you're left with x squared y. Okay? So having this act on a function, this results in the gradient of f. Okay? So that's what we've done so far with the del operator. But now, because this is a vector, I can still talk about using this del operator now maybe on a vector field instead, and it's going to give me a different concept. So I'm going to show you just the general case using R3. If you're working in R2 though, we're going to have to define this because it's a vector with dot and cross product, but I need a third component for cross. So you would just add a z because there's nothing in the z component. So in general, if I have a vector field which has components p, q, and r. And again, if you're missing r, then just put a 0 here, where these functions p, q, and r are differentiable. Then we have two definitions. The first definition is the divergence of f is defined by the following. We write div of f to say take the divergence of f. You're going to go ahead and take this del operator and dot product it with the vector field. So the result of this will be a scalar function. Okay. So in this case, you'll end up with something that is just maybe still has x, y's, and z's, but it is not a vector when I find the divergence. The second thing I can do with two vectors is I can take the cross product. this will define the curl. So the curl of F is defined by this one. Since it's a 4-letter word, we write out the whole curl and we input that vector function. Make that look a little nicer up top. And this is given by taking the del operator, cross-producting it with F. Okay. So the result of this is a vector function. So hopefully the names kind of give inclination as to what they're calculating. Divergence, if you think of that, it's the likelihood of it to go off. Think of divergence when we talked about whether a series was divergent or convergent. Divergent meant it blew off to infinity, or it just kept going back and forth between a number, but it didn't go to one set thing. So divergence is actually going to calculate how likely it is for a point to move from that spot if I start there in the vector field. So if it has divergence, it's likely going to explode and move out of that direction. Where curl is, again, what the word curl sounds like. It's your likelihood of basically just moving in place. So you would kind of rotate around. So giving you kind of examples of this with a water stream as our vector field. When you've got that downhill current, it's going super fast, that would have high divergence. But it wouldn't have curl because you're not staying in place. But if you start in a little eddy or like a little whirlpool, well, that's something that would have curl because you're staying in place there and just rotating around. Okay, so this is giving a concept to that bit we did way back in the beginning where we talked about source-free and rotational vector fields. So we're going to go ahead and now calculate a bunch of these, but then give further definition to each of them. So depending on the type of vector field you're working with, you can get some good properties. So let's look at an example. We're going to let F be the gradient vector we just found. So the function that I'm working with is a triple. It's x squared yz. Then we've already calculated F to be exactly what we have up here, 2xyz, x squared z, and x squared y. Okay. So for this vector field, I'm going to go ahead and find both of these components. We're going to start by finding the divergence of F. So what I want to do is I want to take the del operator and dot product it with this vector field. Okay. Divergence is going to be dot product. Curl gives you a vector because the result is the way that you would rotate or curl in place. So you can think of like, if you've ever seen like a little ball, like plop it in a whirlpool, it could rotate at one angle, it could rotate just at like a 90-degree angle, it could rotate sideways, it can do a bunch of different things. So curl results in a vector. Divergence just gives me the likelihood of moving out of that spot. So it is going to result in a scalar function, which is a single number. So here I'm going to take my del operator and I'm going to dot product it with this vector that I just found. Okay. So that means I want to take the first pieces and multiply them together. So essentially what that's doing is I'm going to find the partial with respect to x of the first component. Then I do the same thing with the middle term. I find the partial with respect to y of the second component. And then last but not least, I find the partial with respect to z of the third component. And I add all of these together. So in the first piece, the partial with respect to x, partial of that is 1, so you're left with 2yz. Here, this has nothing to do with y, so it's 0. This has nothing to do with z, so both of these are 0. So the result is the vector function 2yz. So the result is the scalar function 2yz. So the divergence depends on the point that you're at, which is still okay. You can think of if you're at the origin, you're not going to move. You're stuck in place because y and z are both going to equal 0. But the further out you go from the origin, the more likely it is for you to move and get exploded off that point. So that is our divergence. Now let's do the second operation. Let's find the curl of this vector field. So this I need to take a cross product for. And remember, when we do a cross product, since it's been a while, we've got to find the determinant of the matrix which has I, J, K. I put my del operator first because that's first in this definition. And then I put my vector field F below that. So here is my vector field F. So this piece is 2xyz. This is x squared z. And then this is x squared y. And I want to take the determinant of this thing. Okay. So this results in 3 smaller determinants that I have to do. So I get something times I minus something times j plus something times k. So that's doing that expanding along the first row. So when I go to find the first one, again, I strike out everything in the first row and the first column. And what's left is the partial with respect to y. And I messed up and put y twice. That should be the partial with respect to z. And then this is x squared z, x squared y. Okay. For the second one, I do the same thing, but now I strike out this middle. And so I'm getting the partials with respect to the opposite variables. So partial with respect to x and z. And then the pieces underneath them. And last but not least, same thing for the third. So I'm dealing with z. That means I'm taking partials with respect to x and y. And then the functions corresponding to them. Okay. So I got everything I need to now go through these. Again, you can go ahead and keep doing IJK, but at this point, I'm now going to go back to that vector form. So for the first one, I multiply the main diagonal, subtract the off diagonal. So I'm going to take the partial with respect to y of x squared y minus the partial with respect to z of x squared z. The middle component, you just have to be careful. You have that extra minus sign from doing the expansion. So main diagonal minus the off diagonal. So we're going to take the partial with respect to x of x squared y minus the partial with respect to z of 2xy z. And then last but not least, same thing in the third component, product minus the product. So this is the partial with respect to x of x squared z minus the partial with respect to y of 2xy z. Okay. So now it's a matter of taking these partial derivatives. So the partial with respect to y is x squared. Partial with respect to z is x squared. And the middle component, partial with respect to x, would be 2xy. And then the partial with respect to z, well, that's a 1, so you get 2xy. And then the partial with respect to x would be 2x with the z attached. And the partial with respect to y, this becomes a 1, so you get minus 2xc. So it ends up being that everything cancels out, and the result in this case is the 0 vector. Okay? So what ends up actually happening here, if you think about the two concepts, divergence and curl are kind of conflicting things that can happen. So if I'm going to move from that spot, I'm not going to curl in place either. So it's typical that one will be 0 and the other will be something else. So in this case, because I actually had some divergence that is point dependent, it's not likely that I'm going to curl in place. So that's why I end up with the 0 vector. Now, realistically, what ends up happening is because I started with a function and I found the gradient vector to figure out my vector field, this will always happen that the curl is equal to 0. So think about what it means if I'm finding a gradient vector. We know that represents a conservative vector field. So in the case of a line integral, I'm conserving energy. Well, if I have curl, that's my likelihood to rotate in place. That's not conserving energy. So always when I have a conservative vector field, the curl is going to equal 0 for that. And what I'm going to actually do is prove this because it's pretty straightforward. So this will always happen when I start with a function, find the gradient vector, and find the curl of it. So this theorem states, let f be a function of x, y, and z. Let this be a function with continuous second order partial derivatives. Then the curl of the gradient vector of this function will always result in the 0 vector. Again, the result has to be a vector. So like I said, this is something I can give you the proof of pretty quickly, and it'll hopefully make sense. But if I find the curl of a gradient vector, to find my curl, I take ijk, and I'm going to take my del operator, and I'm going to dot product it with this vector, which is the partial with respect to x, the partial with respect to y, and the partial with respect to z. Okay. Because again, just off to the side, just to show you, this again is that vector of partial derivatives. Okay. So I'm not going to bother doing all of the 3 mini matrices that I need to take determinants of. I can go ahead and show you here. In the first component, I go ahead, strike out this row, wrong tool, and then I strike out this row. So I'm going to take this product, which starting with that one, I would take the derivative of the partial with respect to z with respect to y. So first I'm differentiating with respect to z, and then with respect to y. And then I subtract this derivative, which is the partial with respect to y, and then z. Okay? And kind of doing each of these simultaneously, we know when we start with a function and then take mixed partials, these are going to be the same thing. So the first component is going to be 0. Moving on to the second component, that means I block out this column instead. And to go ahead and figure out my first component, I would multiply these two together. And I also get a negative in front because it's the second component. So that first piece is I'm starting with the partial with respect to z and then taking the partial with respect to x. Doing the same thing here, and you see we get the other mixed partial. So x and then z. But because I start with a nice function, this ends up also equaling 0. Third piece, now I strike out this one. Taking this partial, that tells me first with y, then with x. Subtracting this one would be first x, then y. But same thing again, because this is a function I started with, and then I found that gradient vector, the mixed partials are going to equal each other. So all three components end up being 0. So the curl gives us the 0 vector. Okay. So in this case, I now get another definition for how I find a conservative vector field. So basically, instead of having to check the mixed partials are equal, that's exactly what this is doing. It's guaranteeing that all the mixed partials are exactly the same. So if I have a vector field and I want to check if it's conservative, I can go ahead and evaluate the curl, and it better give me the 0 vector. So as a result of this, we get the following theorem. Doesn't have a name, something you just get to use the result of. So this tells us if f, the vector field, is defined and has continuous partial derivatives, in R3, then the vector field f is conservative if and only if the curl of the vector field is the 0 vector. Okay. So if f is conservative, the curl is 0. If the curl of the vector field is 0, the vector field is conservative. And again, hopefully that makes sense based off the name. If you have a tendency to rotate in place, there is no way you're conserving energy. So you cannot have a conservative vector field. So this gives us definitions then for what happens based on the curl and the divergence of a vector field. So if I take the dot product and it results in 0, that tells you that the divergence is 0. So then we say the vector field f is said to be source-free. So this is just saying that the divergence of the vector field is nothing. You're not diverging, so there's no source that's pushing you out. It's kind of basically like there's no like pole or magnet in there that's just telling you get away from here. And then if you have The cross product is the 0 vector. Your curl is nothing. So then the vector field F is said to be irrotational. So this is saying the curl of the vector field is nothing in any direction. So you are not rotating in place. Okay? So let's try some examples. We're going to work with vector fields that we can go ahead and plot and have actually plotted way back in the beginning. So we're going to go ahead and see the curl and divergence for each of these. So we're going to do 2. Let's let the vector field F have 2 components, x and y. You can definitely calculate the divergence of this because it's just the partial of each. But again, to do curl, you need a triple vector. You need 3 components. So in this case, what I need to do is I need to give it a C component. And the easiest C component is going to be 0. I don't want to introduce something else like a variable because that's not the same vector field. In theory, you could use like 5 because then that would be just in a plane parallel to the xy plane. But the easiest one is just make it 0. So in this case, our vector field would be this. So this piece makes it, since we have no z component, so putting 0 we can take the cross product. To compute the curl. Okay. So it's just kind of a nice shortcut of this. So let's go ahead and for this vector field, find both of the components. We'll start with the divergence. So this is going to be our del operator dot product with the vector field. Again, you can do this in 2 dimension. You don't need to do it in 3 dimension. So you can take the partial with respect to x, the partial with respect to y only. But just to show you, when you do the partial with respect to z, it does nothing because this is x, y, 0. Let me scoot it over a little bit so it's not crowding that notation. So going through these, first component would be the partial with respect to x of x. And then I add to that the second partial with respect to y of y. And then the third. So partial with respect to z of nothing. So you can see it does nothing. So this ends up being 1 plus 1 plus 0, which gives us 2. So this tells me the divergence is the same at every single point. It's not point specific. It's always going to be 2. But because this is not 0, this is not source free. Okay. So now let's do the curl of this vector field. And instead, I'm going to take the cross product of these 2. So again, set this up. I, j, k are del operators. And then our vector field is x, y, 0. Okay. So going through each of these, I'm going to go ahead and just jump right into that final piece. Because again, on the iPad, it's nice. The first component I cross out. I take the product minus the product. So this would be the partial with respect to y of 0 minus the partial with respect to z of y. The second piece, I need to put that extra minus sign and then go ahead and get rid of those. And I ignore this piece. So now I do the product minus the product. So that's the partial with respect to x of 0 minus the partial with respect to z of x. Third component, block this out, and then I do product minus product. So that's the partial with respect to x of y minus the partial with respect to y of x. And so those are all of my pieces. Now I go ahead and take these derivatives. Well, that first piece, that's 0, that's 0. So the first piece is 0. Second piece, 0 and 0. So again, a big old 0. And third piece, 0 and 0. So what do you know? Our curl is exactly the 0 vector. So this would mean the vector field is irrotational. And also because the curl is equal to 0, it's conservative. So this vector field is irrotational and conservative. So what that means is way back up here, you can find a potential function for this. So a function whose partial derivatives are exactly this. Okay. To give you just insight as to what this looks like as well, we actually already plotted this. So what we found out is if you found the point at 1, 0, it ended up being a vector in this direction. Here, the vector shot off. And then we also did points along that unit circle just to see. But no matter the point you picked, it was diverging away from the origin. Okay. So here, the divergence of this vector field is always going to be 2. And the curl of this vector field is the 0 vector. So essentially, you have some source here in the middle that's causing everything to repel from that point. Okay, so this is why it's not source free, but also you can see you're not rotating in place because you're just going off and then continuing to move away from that source. So it's some kind of energy that's emitting from here. Okay. So let's go ahead and look at another vector field, just to refresh you. So you have the vector field here. If you want it, this vector field was xy. Let's try a second vector field. We're going to let f be defined by negative y x, which again, just add that third component to make z equal 0. Then, if I calculate the divergence of this, it is the dot product and again, you can just do the 2. So instead, just to show you, because they give it to us as 2. You can just take the dot product of these things as well. Okay. And then I'll even add in just that extra piece here. It is the del operator dot product with f. If you feel confident taking these partials, props to you, go ahead. But again, when you start getting complicated, I would recommend taking it step by step. So let's go ahead and write this out. I need to take the partial with respect to x of negative y. And then I want to take the partial with respect to y of x. So in this case, that is 0 and 0. So the divergence is 0. So I'm not likely to leave this area essentially. Now if I find the curl of this vector field, that's instead the cross product. So I'm putting my ijk, my operators, and then my vector field is negative y, x, 0. So we'll go ahead, jump right in, cross out, cross out. Then we go ahead and do product minus product. So this gives us partial with respect to y of 0 minus partial with respect to z of x. Now moving on to the second component, strike this one out, put a minus in the middle, and I want to do product minus product. So partial with respect to x of 0 minus partial with respect to z of negative y. And then third component, strike this out, product minus product. So partial with respect to x of x minus partial with respect to y of negative y. So I have everything I need. This first one, that's 0. That has nothing to do with z, so the first component is 0. That's 0, nothing to do with z, so the second component is 0. And here that's 1. This is negative 1, so you get 1 minus negative 1, which gives me 2. Okay. So my curl is not the 0 vector. However, the divergence is 0, so we can say this vector field is source free. But it is not conservative. Or it is not irrotational. So if you remember plotting this one, what we ended up getting was a bunch of vectors like this that traveled on that unit circle. They were all the same length. And so you see, you would essentially curl in place. So this vector field is given by negative yx. The divergence of this vector field is nothing, because again, if I drop my point here, I'm basically going to just keep following around the same circle over and over and over again, and I'm staying in place. So the curl of this vector field results in an actual vector. Okay? All right. So the very last thing I'm going to do is we're going to look at two vector fields. We're going to go ahead and determine which one is source free, which one's irrotational. And for the one that is irrotational, we know that means conservative. So we're going to go ahead and then find that potential function. So we're going to get even more practice with that in this next example. And this will be our final example for this section. We're going to let the vector field F1 be given by 2 xyz, then x squared z, and then negative y z squared. And then F2 is going to be given by 2xy, x squared, 1. First thing we're going to do is we're going to determine which vector field is source free and which is irrotational. Okay. So we're going to work on source free. I'm going to calculate the divergence of each of these. And essentially I'm going to just split it right down the middle. We're going to find each of these. So starting with the divergence of F1. I'm going to take that del operator and dot product it with this vector field. So partial with respect to x, partial with respect to y, partial with respect to z. At this point, hopefully you can see exactly what you need to do without actually writing that out. You're going to take the partial with respect to x of the first component, add the partial with respect to y of the second, and then the partial with respect to z of the third. Okay. Partial with respect to x is 2yz. Partial with respect to y is nothing. And then partial with respect to z is negative 2yz. So this ends up canceling out and gives us 0. Let's scoot that over a little bit. Then let's find the divergence of the second vector field. And so again, we do the same thing. We're going to take the partial with respect to x of the first piece, add this partial with respect to y of the second component, and the partial with respect to z of the third. Partial with respect to x is 2y, and then partial with respect to y is 0 and 0. So this ends up being 2y. So between these two vector fields, the one that equals 0 is source free. So vector field 1 is source free. Okay. So automatically that's going to tell me that vector field 2 is the irrotational one because you're not going to be source free and irrotational. But again, I'm going to go ahead and calculate the curl of both of these. So again, just going to cut this in half, continuing down to do so. So finding the curl of the first vector field, plugging in those pieces, this is 2xyz, x squared z, and negative y z squared. And then I need to move this down a little bit because I need to put my del operators in the middle. So this one, I'm just going to directly take the partial derivative so I don't have to write everything out again. So in my first component, we strike out. Then going through each of these, I'm going to take the partial with respect to y, which is negative z squared, and subtract the partial with respect to z, so that is minus x squared. Okay. So immediately, those don't cancel out. I know this one's not conservative. That's okay. We'll keep finding the other pieces. The second component, I put a minus and strike this out. Now doing those two, at least thankfully, the partial with respect to that is nothing. And the partial here with respect to z would be 2xy. And then in the third component, probably going to need a little bit more room. Just scoot that over. We go ahead, strike this one out. And now I do partial with respect to x, which is 2xc, minus the partial with respect to y, which happens to be the same thing, 2xc. So this ends up being negative z squared minus x squared. That turns into positive 2xy, and the third component is 0. So you see divergence is nothing. That is source free, but you do have a curl to this. If I go ahead and calculate the curl of this vector field, doing the same thing, ijk, our del operator, and then plugging in that vector field, which is 2xy, x squared, and 1. Immediately jumping into each of these, cross out. Going to take those partials. So partial with respect to y is nothing. And then minus the partial with respect to z, well, that is also nothing. So looking okay so far. Now for the middle component, strike this one out. I need to put that minus sign. And then we go ahead, partial with respect to x is nothing. And then partial with respect to z is also nothing. Okay, third one, block this out. Partial with respect to x is 2x. And then partial with respect to y is also 2x. So thankfully, this does end up equaling the 0 vector. So F1 is source free. F2 is the one that's irrotational. Okay. So now that we have that, second question is which vector field is conservative? And so that's exactly F2 because the curl is the 0 vector. We're not wasting energy rotating in place. So F2 is conservative since the curl of F2 is the 0 vector. Okay. And then again, just to get this practice, because we haven't found a potential function yet in any of our videos for a function with 3 components or a vector field with 3 components. The last thing we're going to do is for the vector field that is conservative, find a potential function. Okay. So just copying down F2. This is the vector field 2xy, x squared, and 1. Since I know this is conservative, that tells me the first is the partial with respect to x, the partial with respect to y, and the partial with respect to z to make this the gradient vector of some function. Okay. So what I want to do is, again, utilize these partial derivatives to go ahead and find my overall function. So this one's a little more complicated than our other pieces because I have this triple. So when I integrate my first one with respect to x, instead of getting a function of y, you're instead going to get a function of the other two variables that you haven't used. So you kind of see we had this process of we integrated, then we differentiated, matched up. And then we'd integrate, and that gave us the missing piece. Here, we're basically going to have to do that now another time. So I'm going to integrate, then I'm going to differentiate with respect to one variable, match stuff up, but then I'm going to have to integrate again and do the same process again. Okay? So with this, since the first component is the partial with respect to x, what I want to do is then integrate with respect to x. So our actual function is the integral of this with respect to x. So hopefully the antiderivative with respect to x isn't too bad. This would be x squared over 2. So that just gets divided out. So it gives us x squared y. And again, we normally get a constant when we find an indefinite integral. But here, you're going to get a multivariable function because I did not deal with y and z at all. So the reasoning for this is if I took the derivative of this with respect to x, because it does not involve x, it's 0. So that's the most general antiderivative. Okay. Now, I've used this first piece. I want to move on and utilize the second piece. So I'm going to differentiate this with respect to y and see what happens. So then, since my derivative with respect to y, I know is exactly equal to x squared. That comes from my original vector. And my most general function right now is x squared y plus g of yz. And I need to figure out what this is. I also get that the derivative of this function with respect to y is x squared. And then this would be the partial derivative of this function with respect to y. Okay. So these two things better equal each other. So that tells me x squared is equal to x squared plus gy. And so matching up both sides, I've got nothing else over here. Those two things are equal to each other. It tells me the partial with respect to y of this function is just equal to 0. Okay. And again, my whole goal is to figure out what does this end up having to equal. So now I have its partial derivative with respect to y. We'll integrate this with respect to y to find the actual function. So the thing that I'm looking for is the integral of this with respect to y? Well, the integral of 0 is nothing, and then again you would get a plus a constant, but instead what you get is a function of the other variable I still not have used. Okay? So what I can do is I can basically at this stage now update this function. This has nothing to do with y, it's instead purely a function of z for now. So where I'm sitting, this is equal to x squared y plus a function of z. So this I've been able to update to just h of z. Okay. So going back up here, I've used this piece, I've used this piece. Now I want to utilize the partial with respect to z. So since we know the partial with respect to z of our function is 1, and if I take the partial with respect to z of this piece, well, that's nothing. And then the derivative of h prime, or h of z, is h prime. Okay? So what I get in setting these two equal to each other is 1 is equal to h prime of z. So this tells me h prime of z is 1. So h of z is the integral of this with respect to z. So the antiderivative of 1 is z. And then at this stage, I've run through every single variable. So now I just tack on my constant k. So this gives me all of the pieces I need. I now know exactly what this component is. So the most general potential function is the following. It is x squared y plus z plus k. So again, now I get to replace this just by z plus k. So what I can do, I can definitely check that this does work out. So if I find the gradient vector of this function, the partial with respect to x is 2xy plus nothing else. Partial with respect to y is x squared, and partial with respect to z is 1. So indeed, it lands me back at that original vector field. Okay. So we'll see in another section another way that this comes useful for us when we talk about some of our other special named theorems. But we're going to switch this up from here, and we're actually going to talk about surface integrals. So we're going to kind of take this up a notch from line integrals and go into two-dimensional surface integrals.